ways that work with products from several HPC companies, including Cray, SE, Sun, HP, and NEC. In addition to an extensive background in the hardware history of the HPC industry, Dr. Reyes has worked in several industry segments, including oil and gas, weather, aerospace, and government research. Dr. Reyes received his BS in mathematics from Arkansas State University and an MA and PhD in mathematics from the University of Texas. So let's welcome David, please.
Where's the clicker? Oh. Thank you, Dr. Panda, for allowing me to speak here. I'm not sure that y'all will enjoy it very much because most people tell me that I speak two languages, bad English and really slow English. So if I only get through one slide, that's probably within expectations. So, as with the Intel presentation does, I have to read this to you. And of course, you already know by my speech patterns that if I read that to you, we'd still be here at the end of my 30 minutes. So I'll just tell you that basically it says you can't trust anything I say. So just accept that and we'll have a good time. And not only that, you can't hold Cray anything that I might say because I don't know what I'm going to say either. So it's always an adventure. It was mentioned that I started with thinking machines. And this type of curve, I'll explain it, was very, very important to us. It was the early days, and those of you, I don't know if you guys were old enough to have it run on a connection machine. Okay, one or two, all right. In those days, you recall that we used a 1-bit processor in our original machine. And when we were short of money, our managers wouldn't even give us the 1 to work with. So we had to always use the 0. It was funny back then. But one of the things that I've been trying to do ever since those days is have a very flat performance for a lot of the areas of the system. If you recall, we were one of the first ones to have a parallel list. Now, you may not think of this as a scientific language, but we actually tried to convince the scientific community that Lisp was a good language. We quickly learned that no matter what you're going to program in the scientific community, they're always going to call it Fortran. So you might as well not even try. Just call whatever you program in Fortran, and they'll be happy. But we tried to have a very good development language. We tried to have a nice management infrastructure, even though it was pretty radical at that time to have the number of processors that we had. And that has actually been carrying over all the way through my career. And at this point, the cluster group is targeting a line like this, a flat curve regardless of the number of nodes for a lot of the areas around the cluster. In particular, things like the admin. We don't think about it all the time, but if you try to use PDSH, PDSH is a nice parallel capability. It's just not scalable. So our cluster systems are designed so that you have a flat management capability so that you can set the processor speed, the max processor speed, in one place, and it will automatically be flowed down to the entire system in just a matter of a second or so. So we have tried in many areas and now you know why. Oh, there. We've tried in several areas of the administration to keep this a very flat scaling. Monitoring. This is something that is oftentimes under considered whenever you're putting together large clusters. Monitoring tools and clusters tend to be a bunch of independent tools. What we've put together within the cluster group is a methodology to allow monitoring that does not add additional jitter to your runtime environment. Support. You don't want more questions coming to you because of broken systems just because you double the number of nodes. So those are all considerations that we have tried to put together within our environment. And the one that we've been working with Dr. Panda on recently is this runtime environment. Through our research over the last couple of years, we've identified 2 or 3 areas where the runtime system needs to be improved in order to scale highly available clusters into the 10,000 node range. So these are important considerations. And within our group, we make the statement, it is a laughable and a simple statement, that not for the algorithms, but for the rest of the system, the cluster should feel like a Linux workstation. It should be no harder to administer a cluster than it is a Linux workstation. It should be no slower to upgrade an OS than a Linux workstation. And so as you talk to us, that's one of the things that we will try to impress upon you. So the foundation for this is we've put together a hierarchical infrastructure for our demons. We both flow down the boot image and the boot management from a single point up in the management server through a set of sub-management servers and then all the way down to the compute node. The reason we do this is because we use a diskless boot, and we have proven that we can boot nearly 2,000 nodes in less than 5 minutes using a diskless boot. Using the same infrastructure, we collect performance data from back here, flow it up through out-of-band infrastructures into the management server so that you can get your monitoring data directly from the management server without adding any additional jitter. And as you get larger and larger systems, that jitter becomes a big issue. And so one of the things that the first thing we've been working with Dr. Panda on is the job startup. And just as Slurm has a similar parallel infrastructure to this, we've been leveraging Dr. Panda's work and his students to try to get the job startup to leverage this so that a user can run a job across 1,000 nodes and not have to wait 10 minutes for the first result to start coming through, which is sometimes happens on large systems. So our emphasis is on that, and we're trying to mirror this capability There are a lot of complexities in this when you talk about the caching of the data caching, data replication and stuff. But this is our goal, is to get every piece of the stack so that it mirrors that hierarchical structure. One of the differences between cluster systems and other systems is that the stack is robust. For some reason, you can't get 3 people in the room to agree on what the best compiler or the best MVI is. So what we do is we provide an environment to actually quasi-support all these different pieces. Dr. Panda's piece is over here in this little box, but our customers, some of them like still run PDFs, some of them are adamant about Slurm, some of them are adamant about the LSF, and in some places in Europe, grid engine is still big. So one of the things that we're trying to do is establish a good baseline for what fast job startup is. And as Dr. Panda has mentioned, at this point it involves Slurm and is in its food product. And we hope that this flows out and we can begin getting the rest of the community aware that when you have large-scale systems, you need to have this hierarchical infrastructure, as well as some other runtime enhancements in order to make it efficient. We have a robust suite of compilers. We have our own compiling environment we support. We also support the Intel cluster and the PGI cluster toolkits, as well as the GNU tool chain. And we are now selling a large number of CUDA systems. In fact, if you look on the website, the Cray website, or some of our announcements, you'll see that we announced our Storm product, which is, as was discussed earlier, an 8 GPU in a 2U configuration, so that you get over a petaflop in 4 standard graphics. So you're starting to get up into fairly dense infrastructures when you talk about those kind of configurations. So unlike, we like to push on Dr. Panda's group or some of these people in the resource management, our perspective is a little different. We can't just provide a piece of the puzzle. When we start pushing, it's so that we get at least one string all the way from top to bottom so that it scales and so that it's usable. What we believe right now, as I said, we try to have at least one stream, and all of these have to be integrated into a scalable base. If you have one piece of that entire stack that isn't scalable, it makes the rest of it not scalable. And that's a big trick. There's a lot of work that goes into that. If your job startup is fast, but then your dynamic linking of your libraries is slow, guess what? You still have a slow startup. If you try to copy all of your libraries out to each compute node, and then you want to do an update, well, if you look at the Intel compiler suite, that's over 1 gigabyte just to update your library out to each compute node. Which means either you better have a parallel copy, i.e. you need an infrastructure there, which we'll talk about later, or you have to have a scalable library linking environment. So from our perspective, we attack each of these individual layers and try to get some scalable pieces in that. And we believe that that will allow clusters to continue to consume more and more of the available cycles. So what do we see as the big MVAPICH 2 challenges? We have started on this job startup with Dr. Panda and had some great success. His team is doing a great job on that. But there are some additional things that need to work. For the job startup, with the Slurm as run capabilities, we are seeing users who want to sit down at a keyboard and type srun and start seeing stuff come out immediately. Not wait for the next day to look at partial results. That means that the old thing of taking 100 seconds to start up doesn't flow. So we need sub 10-second startup regardless of the number of nodes that you have, regardless of the complexity. The fact that we have 8 GPUs doesn't matter. The fact that you might have 64 cores in each node doesn't matter. We need that flat job startup. We need to leverage that hierarchical environment if it exists. Right now, a lot of the MPI startups tend to rely very heavily on setting up their entire environment themselves. We're going to have to improve the interaction between the scheduler and the startup so that you get all of the information at startup and you can put it down. And if you listen to some of Harry's talks the other day, they've done a lot of work on topology aware, but one of the things that they have to do is they have to go out and measure the number of hops between each of the processes. We need to be able to pass all of that in from the schedule. One of the things that we've seen right here is that optimizations tend to only be available in one piece of the stack. One of the difficult challenges that you have is when you want to copy a library out. MVAPICH has a very nice runtime environment available for moving data around. But that runtime environment isn't readily available for simple administrative tasks. All of us have probably hacked out a copy routine using MPI run. I don't know how many times I've hacked that out. But simple things like that need to become part of a runtime standard so that you can do big administrative tasks in a standard way across all of your clusters. So that you can copy libraries, so that you can move standard data. A lot of times you have to read in the same file on to every compute node. You need to be able to access that and copy that data and store that data off later if necessary when you write temporary data to disk in a nice, fast, parallel way using an infrastructure to do it. Not rewrite everything yourself every time you have to do something. And a few years back, the open OFED really made life easier. If you watch, if you watch the current OFED environment, I think it's safe to say if you ever have to do it, luster plus OFED is best case nightmarish. Trying to do a luster and an OFED upgrade, any of you that have ever done set up luster, once you get a server set up, how many times do you change it until it just collapses? You never change it. So everybody, the OFED people say, oh, you get this new OFED, just upgrade to this client. It might not be possible. And yet, we keep talking about doing analysis using some of the standard tools. You might not be able to reach your data because it's on the wrong version of luster or an OFED combination. So those are the challenges that the community has that I think Dr. Panda's group could help with. He has a very robust testing environment. He does a really great job testing it. And some of these things, even though they may not be the final answer, we need him to contribute to those things. The one thing that I would ask each and every one of us, I still remember whenever MPI was standardized. I mean, Ms. Saroff mentioned 1993. Hey, I remember those days. And that was painful. Y'all don't remember the PVM versus MPI wars that just raged. And I wonder if it might be time for some runtime environments to become standardized. And some of the other challenges that we're working on is this dynamic linking. Clusters don't like to cluster users don't like to statically link. But if you start a job on 2,000 nodes with dynamic links in them, every once in a while things fail. Your luster can't get the library out to it fast enough. The NSF server can't get it out fast enough. You might not have disk. It is a big issue, and you're going to be seeing things come out of Cray addressing this particular capability over the next few months. Data analysis. We talk about it, but we don't have the infrastructure in place. Dr. Panda is doing a lot of work on a common runtime environment. As we go forward, can we extend that all the way into Hadoop? Can we extend it into some of the time series analysis tools that are coming out, the image processing tools that are coming out? Can we have that common runtime environment so that we know we're going to get performance? And the analytic models, huge issue, a lot of data, some of it's out on old storage systems. How do you take a new cluster, hook it up to an old storage system, and still do analysis of data that compares runs from 5 years ago to what you're getting now to see if your model has improved? And then, once again, I have to say, just remember, you can't hold me to anything. And you can't hold Cray to anything that I said. So, any questions?
Okay, so questions?
So when